Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 4 of the first module of our course on machine learning for earth system science. So, like this first module is about spatio-temporal statistics and we are in the fourth lecture of it. In the previous lecture we considered the geostatistical equation and how it can be expressed as some kind of a stochastic model for spatio-temporal processes. And we came to the conclusion that to incorporate the spatial and temporal autocorrelations between the different variables, we need to use we need to sample them from some kind of joint distributions rather than sampling them individually from individual locations or time points. So, one like we at the end of the lecture we mentioned that one way to achieve that is through Gaussian process. So, what is this Gaussian process all about? So, in today's lecture we will first consider Gaussian process regression, then we will see how the spatio-temporal processes as we considered in the last lecture can be modeled using the Gaussian process, and finally how the inverse problem can be solved by using sampling. So, first of all let us talk about the Gaussian process. So, this Gaussian process is nothing but a probability distribution over functions. Now, that may sound strange because we have considered various kind of probability distributions so far, like for example the Bernoulli distribution. It is a probability distribution over we can say over only two things, maybe the heads and tails of a coin, or if you consider the Gaussian distribution, that is a probability distribution over real numbers where every real number has a probability attached to it. Similarly, there are other kinds of probability distributions. There might be some probability distributions which are over categorical or like categorical quantities and things like that. Now, this Gaussian process is such a probability distribution. It is defined over functions, that is entire functions have a certain probability under the Gaussian process. That may sound strange, but actually it is not so strange. We will try to explain that in a bit. So, now this so what is this Gaussian process used for? This Gaussian process, it may be used to predict the observable at places where the observation is unavailable. What do I mean by that? So, suppose you are so I already mentioned that Gaussian process is a distribution over function. Now, what function? So, since we are dealing with spatial and temporal variables, we will focus only on spatial and temporal functions only. So, like if you consider say the spatial function like this kind of a spatial let us consider this kind of a temporal function over t. Okay. So, this you can call this as let us say x t, or let us say we have a special location like some special field, let us say it is indexed by the latitude S1 and longitude S2, and at different parts like we have like different values of this spatial process. So, the idea here is that this kind of a curve, it can be considered as a temporal function. This can be considered as some kind of a spatial function. So, this function is in both cases is nothing but a collection of values over an infinite number of points. They may be in this case those points are time points. In the right hand case, in case of the spatial function, those points are the spatial points. Okay. So, like when we are talking when we are talking about this x t, we can call it as some kind of function over time, but in reality it is nothing but a very long vector, like the vector at t1, the vector at t2, sorry I mean the observation at t1, the observation at t2, the observation at t3, etc., all the way at till the observation at tn. but this n may be arbitrarily long. So, note that at every time point, at every single time point, I have noted an observation. It is not discrete like T1, T2 and so on. So, basically it is like the points at which this function is evaluated is uncountably infinite. We can look upon this temporal function f as a vector of the observation x, but that vector is it is infinitely long vector. Okay. So, now in this, from this point of view, you can consider the Gaussian process as some kind of a distribution over the functions. Now, suppose you have estimated this kind of a function at different time points. That means what? That means if you have any new time point, you should be able to or you may be able to estimate the value of the observation at that time point. Once you, of course, once you have learned, or once you have been able to parameterize that function somehow. Okay, so that is the most important application of Gaussian process, where it is basically used for interpolation, that is to predict the value of the observable where the observations is not available. It can also be used to generate the global component of the spatio-temporal process. So, in lecture 3 we mentioned that this global component cannot be sampled at individual time points or locations, but has to be sampled from some kind of a joint distribution. Now, this Gaussian process, by being a distribution over the functions, it's actually it's actually being like something like a joint distribution over multiple time points or multiple locations. Okay, so the spatial and temporal autocorrelations can be captured using the covariance function. Now, this Gaussian process, it has a covariance function which will which we will discuss once we come to the formulation of the Gaussian process, and that the task of that covariance function is to capture the spatial and temporal autocorrelations between the different locations and different time points. That is to say, whenever we are sampling any observation from a Gaussian process, the Gaussian process is basically giving us the values at different time points and or at different locations. However, those values will be following some kind of some relation between the it will follow the, or it will respect the covariance between those locations or the time points, which might be known from already from the data. Okay. Now, coming to the actual formulation of this kind of a Gaussian process. Before the Gaussian process, let us first consider the Gaussian distribution. So, the simple Gaussian, the univariate Gaussian distribution, we all know, that is the standard normal distribution, where we have a mean mu and a variance sigma. Now, the same thing can be considered in multiple dimensions also, in high dimensions also. So, instead of having a single variable, let us consider a collection of d variables like this, x1, x2 up to xd. Okay. And now, all these random variables, they can be taken together to form a vector of random variables, which we can call as x. Okay. So, this vector of random variable is nothing but this x itself can be considered as a vector random variable, which is nothing but a vector of individual scalar random variables. Now, what we want to do is we want to define the probability distribution on this x, that is, the input will be a vector, d dimensional vector x, and corresponding to that we will get a value of the PDF. So, this is what that PDF looks like, and so like you might see similarities between the this PDF and the PDF of a standard normal distribution. So, in this case, just like the standard normal distribution has its parameters mu and sigma, this one also has mu and sigma, but the difference is that here this mu, the mean, is not a real number, but it is a vector, it is a d dimensional vector, same dimension as the input x. And instead of having a sigma as a covariance, a variance, we have a full matrix, a d cross d matrix, which we call as the covariance matrix. So, what is that matrix what does it consist of? So, if you consider any element, let us say the ijth element of this covariance matrix sigma, it basically contains the covariance between the random variables xi and xj. Okay. So, remember that x is the collection of these d random variables. So, I take up any two of them, let us say xi and xj, I measure the covariance between them, and that covariance is will be present in sigma ij of this covariance matrix. And you can understand that this is going to be a symmetric matrix, because if sigma ij must be equal to sigma ji, because covariance of xi xj is same as covariance of xj xi, right. And not only is this covariance matrix, not only is it symmetric, but you can actually show that it is positive semi definite. Okay. And because of that property, you can always define its inverse in this way. It is invertible matrix, and you can also, and its determinant will also be non-zero. So, this the problem is that this covariance matrix, its size blows up with d. That is, instead of considering a small number of variables like this, if you consider a very large number of variables, then this covariance matrix it will become d cross d, that is its size is going to be bigger and bigger. As a result, carrying out these kind of inverses or the determinants is going to become more and more difficult. So, the solution in that case is to replace this kind of a covariance matrix by what is called as a covariance function. Now, what is a covariance function? So, the covariance function is that instead of having to store the covariance of the x at different locations, I am sorry, between different variables, what if we can somehow express that difference that covariance using some kind of a function. So, that will happen only if this that is, we can say that it can happen easily if this the covariance is stationary. So, let us explain that in a bit. So, the idea here is that instead of considering a finite set of d random variables like this, let us consider a finite or infinite set of random variables x1, x2 and so on. Okay. So, so basically we are relaxing this to the situation where d tends to infinity. So, we still have the variable x, I mean the vector random variable x, but it has become an infinite vector. So theoretically we can still use this kind of a multivariate Gaussian distribution on x, but the problem here is that we can, because the number of the number of these variables has become so large, we can now no longer do the calculate the determinants and inverses efficiently. Now let us also consider that these d different variables that we are considering, they actually are specific to locations. So, you can say that there is a geophysical variable x which we are measuring at an infinite number of locations. Okay, maybe that is temperature or something like that. Now, if you consider any finite random subset of these locations xi1, xi2 up to xin, so I mean n is any, let us say any integer. So, what we are doing is we are focusing on only a certain number of these or a finite number of these locations, and what we are trying to do is that now we are trying to define some kind of a distribution on them. Now, in the Gaussian process is a model which states that if you consider any random subset of these of such variables, we will get the Gaussian, their joint distribution will still be the Gaussian distribution with a mean mu and a covariance matrix sigma. So, note that the mu in this case will be an n dimensional vector and the covariance matrix will be n cross n matrix. Also note that I am calling these as xi1, xi2, xin. So, you may be wondering what these i's are. So, this is to emphasize that we are choosing any set of n points. that is xi1, that is if I say x1 x2 up to xn, it may mean only the first n points, but by writing i1 i2 in, I am emphasizing it that it can be any n points. xi1 may be 6, xi2 may be 13, xin may be, say, let us say 555 and so on. So, like if you consider any subset of n variables out of all these collection of like infinite variables, like whether you are considering one variable or two variables or 17 variables, whether they are the first variables or the say the fourth and ninth variables or whatever, they will all, their joint distribution will always be the Gaussian distribution. And the now the mu, the mean of that Gaussian distribution is the is the mean function. That is, it is such that whenever you are considering any particular point in space, its mean is to be expressed as a function of that location. So, that if that location is expressed in terms of latitude and longitude, you should be able to calculate some function of that latitude and longitude and get that value mu. If that is difficult, you can simply like consider it as some kind of uniform or constant thing, that is as a you can consider it as a spatially stationary process, which means that mu is equal at all the locations. The more interesting part is the covariance sigma. So, this sigma, this has to be an n cross n covariance matrix. Now, every element of this, rather than actually storing all the elements of the covariance matrix, I will express every element of the covariance matrix as some kind of a function. And if whenever we are considering the covariance between any two variables which are like correspond to, let us say, locations s and s prime, we will say that their covariance follows some kind is a like it is a some kind of a function k of the distance between those two locations s and s prime. So, you may remember in lecture 2 we considered the concept of covariance stationarity, which means that the covariance between any two variable or any two locations is I mean the covariance of a particular variable at two different locations is nothing but the function of the distance between those two locations. So, that is what is happening in this case. So, sigma s and s prime is basically the covariance between the value a, I mean the variable x at location s and location s prime, but that covariance is being expressed as a function of only s minus s prime, that is the distance between the two locations, not of any other thing. So, now the question might arise that what kind of function is k, what function we may use to define this kind of a covariance function. So, there is a set of standard functions for this. So, I leave it as a homework for you to find out about common covariance functions. Okay. So, that brings us to the definition of a Gaussian process. So, when we say that x follows a Gaussian process with mean function mu and covariance function k, this is what I mean. It means that x is a like is potentially an infinite dimensional or like a collection of an infinite number of variables, such that if you consider any subset of them, any random subset of them, they follow the Gaussian distribution with parameters which you can obtain from this mean function and the covariance function. Okay. Any finite subset of locations, they follow the multivariate Gaussian distributions. Now, of course, these need not be locations, these can be time also. That is, in that case, it like we if they are locations, then x you can say it's a it follows a spatial Gaussian process. If it's a time points, then we can say that it follows a temporal Gaussian process, yes, and so on. So, now the relation between x at different locations or different time is represented through this kind of a covariance function. and okay, so what is achieved by this Gaussian process? What is achieved is as follows. Once you have parameterized this mu and k, now you can like sample the value at any particular point. So like as you can understand, it will follow the Gaussian distribution only, with some parameter mu and sigma, which like of course you can calculate using these the mean function and the covariance function. So even if you do not have the observations, once you have estimated the mean function and the covariance function, then you will be able to generate the value at any like any location or any time where you may not have had these observations initially. Okay, so that is how this Gaussian process is used for the purpose of interpolation. So to be more specific, let us say we have the observations at s locations x1, x2 up to xs, and I want to make the prediction at location s plus 1, which is the x of s plus 1. So what I will do is I will generate or I will create a conditional probability distribution for at x s plus 1. So which can obviously be written in this way, like using the standard definition. Now if you consider both the numerator and the denominator, both are effectively joint distributions over random variables. The denominator is a joint distribution over s random variables, the numerator is over s plus 1 random variables. Now because it follows a Gaussian process, so any collection of random variables will jointly follow the Gaussian distribution. So the numerator will also be Gaussian and the denominator will also be Gaussian. Okay, so it the PDF of x s plus 1 conditioned on the observation is actually follows this kind of a distribution, where like its PDF is like is some kind of a Gaussian PDF divided by another Gaussian PDF, and you can actually work out the algebra and find that after doing this division the resulting PDF is still a Gaussian, with the of course the parameters of that Gaussian will change. I mean the mean vector covariance matrix of this new Gaussian will change, but it will still be a Gaussian distribution. I mean the numerator here is a Gaussian distribution, the denominator is a Gaussian distribution, and the result the quotient is also going to be another Gaussian distribution. So what will be the mean and the covariance matrix of this distribution? That is, I leave it as a exercise for you to find out. You can like you basically have to write down the PDFs of both of these things, do a lot of algebra, and you can work it out. Like in case it is difficult, there are always various resources you can look up to, like Chris Bishop's book on pattern recognition for machine learning is a very good reference to follow in this case. Okay, so now we use the concept of Gaussian process in the spatio-temporal hierarchical process model that we considered in the previous lecture. So the data model is always there. The Gaussian process is to be used on the process model. So if you remember, the eta is which we called as the global component, that can be expressed as az plus vy, where z is the latent variable at different locations, y is the set of covariates at the different locations, and a and b are the transformation matrices. That is, they combine the latent variable values at different locations and pass them on to each location. Okay. So these mu and these z, these are variables to be defined over all the locations. Mu is something like the static component, the local component of every location, and z is the latent variable which is also defined over all the locations. Now I can in this version I can sample both mu and z from Gaussian processes. So what does it help us? It helps us in preserving the spatio-temporal relations between the different sorry, not temporal, I mean the spatial covariance or correlation between the different locations. Okay, and these Gaussian processes can be either spatial or temporal, and these mu and z we can decompose them into the spatial and the temporal components somewhat like this. So, let us say that my model is spatio-temporal, that is I am trying to build a model for x s t. So, it follows the Gaussian distribution at any location s and time t, it follows the Gaussian distribution with mean mu s t plus eta s t. And now the mu s t, let us say we have a special distribution, I mean a special component mu s and a temporal component mu t, and mu s t is nothing but a product of these two things. Now mu s may individually follow a Gaussian process and mu t may also individually follow a Gaussian process. So, this is a special Gaussian process which is defined over locations, and this is a temporal Gaussian process which is defined over time points. When I multiply them, what I get is a spatio-temporal Gaussian process which is like I get a spatio-temporal variable which is defined for all locations as well as all time points. Similarly, when we are considering the process model, basically the eta, we know that eta is to be expressed as a of z plus b of y. Now, this z and y is of course the exogenous variable which is not a random variable. Now, z is the random variable which is spatio-temporal. So, we can decompose it as with a spatial component as well as a temporal component, and the spatial component again it follows a Gaussian process, the spatial Gaussian process, the temporal component again follows a temporal Gaussian process. Okay. So, now that brings us to the forward problem of data generation, which we have said that it helps us to create or sample new data or maybe data for the future. So, once we have developed this model by specifying all these parameters of the all the hyperparameters of the Gaussian process and so on, by choosing all these covariance function, the mean function, etc. Choice of these is all lies in the hands of the model designer. Once we have done that, we simply identify a set of locations and time points to generate the data, and then we just keep on sampling mu s and mu t based on the values which have already been generated. Once you have the mu s and mu t, then you similarly generate z st at all locations at all time points in the same way from the Gaussian process zs and zt. So, once again you go on sampling zs1, then zs2, zs3 and so on, and similarly you also go on generating zt1, zt2 etc., and then multiply them together to get zst. And finally, once you have got the z's, then you use them to generate the actual values xst using the data model. This is the data model, right? So, basically you get you just perturb it with the noise and generate the data. Now, the inverse problem. What is the inverse problem? That is more complicated. So, that but that is in a sense more natural also. So, as you can see, the model which we defined here has so many parameters, and where will all these parameters come from? Because what you actually have is the data, the observations, and the covariates also. So, the task when we are trying to build the model, the task is to estimate all these other variables. So, there are two sets, the random variables which are z as well as the various parameters. So, we can estimate the random variables by a process called the Gibbs sampling. So, the process is as follows: you assign initial values to all the variables, and the optimal values are found by repeatedly sampling of each of the variables, keeping the other as constant. That is, you may sample. So, z is a collection of variables at different locations and different time points. So, you can focus on one location, sample its values, keeping all the other z's as constant. Then you sample the value of z at a different location, again keeping all the other of them constant, and so on. So, that is the process of Gibbs sampling. Now, in this lecture I will not go into the details of how exactly the Gibbs sampling is done, but basically you repeat this process for all locations as well as for all time points, just go on sampling new values from these kinds of conditional distributions. And once you have done this, once you have sampled a large enough number of these values for every location and every time point, for all the different random variables that are latent random variables that are involved here, you store those sampled variables and repeat this whole process for many iterations, so that for each random variable you get a large number of samples, and so those using those samples you can get something like a posterior distribution over them, and then you can like select the mode of those samples to get the final values. Okay. So that brings us to the end of this lecture. So the key points to take away is that the Gaussian processes are used to define joint distributions. They may be used to predict values or do the interpolation. The forward model may be used for sampling latent variables and generate and create new data, while the inverse problem to estimate the model parameters and the latent variables may be solved using Gibbs sampling and other parameter estimation techniques. So, we will continue further details in the following lecture. So, that is it for today.